Alright, what's up guys? In this video, I'm going to play with some multivariable calculus, and we're going to be finding the tangential and normal components of the given acceleration vector. So we're given the acceleration vector here, r of t is equal to 5 times 3t minus t cubed I plus 15t squared j. So to do this, you do have to be familiar with how to find magnitude of a vector, dot product, and cross product in order to do it. So we'll work through that. So let's first of all talk about the tangential component of the acceleration vector. So you got the tangential component. So for the tangential component of the acceleration vector, it's just denoted a sub t. And remember, to get that, it's just going to essentially be the dot product of the first derivative of the acceleration vector and the second derivative of the acceleration vector, which is given by r of t. So it's the dot product of all of that divided by the magnitude or the norm of the acceleration, the first derivative of the acceleration vector, which would essentially be r prime of t. So that's how we compute the tangential component of the acceleration vector. The normal component of the acceleration vector is what we calculate after that. And so for the normal component of the acceleration vector, it's just denoted a sub n. And instead of the dot product this time, it's going to be the cross product of the first derivative and the second derivative of the acceleration vector, all divided by the magnitude or the norm of the first derivative of the acceleration vector. So in this case, so we're going to have our magnitude of the cross product of the first and second derivative of the acceleration vector, all divided by the magnitude of the first derivative of the acceleration vector. So clearly the first thing we need to do is to just go ahead and start by calculating the first and second derivatives of this acceleration vector, which again, just find r prime of t and r double prime of t. Then after that, once we have that, we can kind of compute everything else. We can, take the dot product and compute the cross product as well. So we'll take care of that first, then we'll find the magnitude. So let's just find the first derivatives. So we'll do r prime of t first, obviously, and then we'll have to do it again. So if we take the derivative here, what will we get? Well, 5, remember, it's just a constant. We take the derivative of the inside here, we get 3 minus 3t squared multiplied by the unit vector I, and it's going to be plus the derivative of 15t squared with respect to t, which is just 30t, and that's going to be multiplied by the unit vector j. Okay. If you want to, you can also simplify this as if you distribute. So this becomes 15 minus 15t squared I plus 30 tj if you distribute the 5. Now we need to do it one more time. So that was the first derivative. Now I got to do it one more time. So same thing here. So if we do it one more time, well, again, we'll just get the 5, which is again a constant. Then in here, remember, derivative of constant is 0. So in this case, we'll just get basically minus 60. So minus there. Multiplied by I, and then it's going to be plus 30j, because the derivative with respect to t for 30 t is just 30, and then you can just multiply by the unit vector j. And if you simplified it a little bit, it would just be negative 30t I plus 30j. So that takes care of the first and second derivatives. Now, you can pick whichever one you want to do first, because you could do either one of them first. Well, actually, the first thing we need to do is go ahead and find the magnitude of, or the norm of the first derivative of the acceleration vector r prime of t. So we'll do that. And then after that, you'll have everything you need at that point. So you can either choose to find the tangential component of the acceleration vector first or the normal component of the acceleration vector first. It doesn't really make a difference which one you choose to do first. So we'll find the magnitude of the first derivative of the acceleration vector, which is just the square root of the sum of the components squared. So we got 15 minus 15 squared, or excuse me, 15t squared, and then plus 30 t squared. And you want to have a calculator because sometimes the numbers can get a little big. Okay. So we know that 15 squared is 225. So we'll get, I'll use parentheses, we'll get 225 plus 225 t to the fourth, because remember we take these two, multiply those powers, and then we'll get minus 450t squared plus 900t squared. And again, you can check everything in your calculator. And I'm going to check just to make sure everything's right. So let me square that. Yeah, we do get the 900. So remember 30 squared is the 900. And so now we can kind of finish simplifying this down. So you got the square root this time. And okay, so we can just write this as 225t to the fourth plus 450t squared plus 225. Now remember, this is essentially going to give us the 15 plus 15t squared. Okay, if we actually solve for that part right there, that's essentially what it's going to give us. So in this case, we'll have the square root, and we can just put the 15 plus 15t squared back in there. And that gives you that. And we know that because it gives us on the front. And then we know when we simplified, we did have the plus 225 on the back end. So we can say that the magnitude of the first derivative of the acceleration vector r prime of t is just, if we take the square root of all of this stuff that's being squared, we just get 15t squared plus 15. Or if you want to, you could just factor out a 15 and write it as 15 times t squared plus 1, which is the same thing because you would distribute the 15 in there and you get that back out. So that would be the essential magnitude of the first derivative of the acceleration vector. So we took care of that part. And so now essentially what needs to be done next is you can either, again, pick which one you want to do first. You can do the tangential component, you can do the normal component. It doesn't make a difference which one you want to do first. But we'll need another sheet for that. So let's get another one. I'm going to do the tangential component first. Doesn't matter which one you do first. I'm just kind of randomly choosing. So for the tangential component, the acceleration vector, that's a sub t. And it's going to be equal to, again, the dot product of the first derivative of the acceleration vector and the second derivative of the acceleration vector with respect to t, all divided by the magnitude of the first derivative of the acceleration vector, which we ended up getting. We already know what that is, so we compute the dot product. So remember, the dot product, let's say we have two vectors u and v, so it would be the magnitude of u multiplied by the magnitude of v multiplied by cosine of the angle between them, which in that case would just be theta. So that's the actual definition of the dot product. So it's the magnitude of u multiplied by the magnitude of v multiplied by the cosine of the angle between them, which in that case is theta. And so let's say I have two vectors u and v, for example, that are two-dimensional. let's say that, for example, well, then that's just going to be u1 times v1 plus u2 times v2. And if we wanted to step it up to a three-dimensional vector, it would essentially just be u3 plus v3. So that's how you calculate the dot product. Okay, well, let's do that. So we're working on the tangential component right now. So we got 5, 3 minus 3t squared, I, plus 30tj. And I'll dot that with the second derivative, which is what I have here. So I'm just working on that part now. And again, if you look at this part up here, notice I've distributed the 5, but I can pull it out in a sense because it's going to make things a little easier to simplify. So sometimes you can just factor stuff out. So it's easier to simplify. So do that as you may. As long as you factor stuff out correctly, it doesn't matter. So in this case, we got negative 30t I plus 30t, 30j. Notice how I kind of close everything up. And now we divide that by the magnitude of the first derivative of the acceleration vector, which again was just 15 times t squared plus 1. Okay. Now we simplify. So let's just keep going with this. Okay, so, all right, well, looks like we'll get, and I'll use parentheses, so it looks like we'll get negative 150 multiplied by 3 minus 3t squared multiplied by t, and then we'll add that to 900t, and then we divide all of that by. We divide all of that by 15 times t squared plus 1. Okay, well, as you can see, we have a 15 here, so if you want to, so you can cancel out the 15, you could probably just try to factor out, see if you can factor out a 15, which you know you can do, because if we factor out, so let's say we got negative 150, so we know we would get negative 10, because negative 10 times positive 15 is negative 150. So you can factor out a 15 such that we can actually cancel out the 15 in the denominator. So now we just get, basically, if we cancel out if we factor out a negative 15 and cancel out the 15 below, so we'll just get negative 30t plus 30t cubed. If we factor out a 15 from that part, so that's just going to be 900 divided by 15 gives us 60. So then this would be 60t. And we canceled out the 15. There was still a negative attached to it, so I just brought the negative to the front. And so now down here we got t squared plus 1. This is what we got. Okay, so we can do some further simplifying. Okay, so this is just going to be 30t cubed plus 30t all over t squared plus 1. If we factor out a 30t, that'll leave us with the t squared plus 1, which can also be canceled. And again, you can always check to see if you factor something correctly by distributing it back in. So for the 30t cubed plus 30t, notice if we factor out a 30t, then I guess I'll put it here. If we factor out, let's say we factored out a 30t, for example, well, then that must mean that we would have the t squared plus 1 on the inside, which we can cancel. We can validate whether or not we factored that correctly, because if we distribute the 30t in, well, 30t times 30t squared is 30t cubed. And then if we distribute it in for the one part, we would get the 30t. So we know that this can actually just become 30t multiplied by t squared plus 1 all over t squared plus 1, which we know those can cancel, thus just leaving us with the 30t. So therefore, we can say that the tangential component of the acceleration vector is just 30t. So that's the answer for that one. So that's the acceleration vector, or the tangential component of the acceleration vector. Okay, so that's that. And now the last one was the normal component of the acceleration vector, which we needed to calculate next. So we're looking for the normal component. I think I spelled component wrong earlier. I think it's 2 n's, I believe. Is it 2 n's or just 1 n? I don't know. I don't know. I got good math and physics skills, but I guess the spelling skills eluded me. Okay, so however you spell component, not entirely sure, but now remember what the normal component of the acceleration vector is. So that was, again, just going to be that a sub n part. And this time, again, it was just the magnitude of the cross product. And it's really well, it's a little bit different than the curvature formula, remember, which was the magnitude of the cross product of the first and second derivative of r of t divided by the magnitude of the first derivative of r prime of t, all raised to the third. The only difference is, in this particular case, we won't be cubing our magnitude of our first derivative of the acceleration vector. So that would be the only difference, but it looks very similar to the curvature formula. So this is what we're working on now, and we just divide all of that by our first derivative of our or the magnitude of the first derivative of our acceleration vector. So I'm just going to continue to look at the information that we have here to continue this. So remember, to find the cross product, you use the matrix method. And so essentially what you do is you set up this 3x3 matrix. So when we set up the 3x3 matrix here, we just simply take the components of the first derivative of the acceleration vector r prime of t and the second derivative of the acceleration vector r double prime of t, plug them in to this 3x3 matrix, where the top row will be those unit vectors I, j, and k. So we'll put those in. So we would have I, j, and then k, and then we just stick in the components. So it'd be 5 times 3 minus 3t squared. The second component, remember, that was 30t, and then it was 0, and then it was negative 30t, a positive 30, and then another 0. And now we calculate the cross product using that matrix method. So we'll finish that up. So essentially, remember what you do. We need to eliminate the first column and the first row containing the unit vector I to get the corresponding 2x2 matrix. And in that case, we just get 30t, 0, 30, and another 0. And the better you get with a cross product, the less steps you have to write out. So just for the purposes of the video, I'm writing everything out. But once you get the multivariable, hopefully by that time, well, once you've kind of digested the dot product, cross product stuff, and you're kind of good with the vector stuff, and you can actually write down less steps. So now we eliminate the second column in the first row. The first row is always going to go, but when you're actually expanding this out, it's going to be the columns that are going to be canceled out. So you would cancel out the first, second, and third column, but the first row is always going to go because it has the unit vectors in them, or in the first row. So in this case, if we do that, we get 5 times 3 minus 3t squared, 0, negative 30t, and then we'll have another 0. And remember, it's I minus j plus k. Now, again, the signs on all of that can change depending on what you get out once you've done everything. And so now, again, the first row is going to go all, in this particular case, but now since we are down to the second part, we need to get rid of that third column. So in that case, we got 5 times the 3 minus 3t squared, and we're essentially gonna, I'm sorry, that's gonna be squared on the inside, and then we will have our 30t here, and then negative 30t, and then another 30 on the outside there, because the third row there was just, or the third column just contained the k and then 2 zeros. Now hopefully you should see that for each of these parts we're going to get 0, because if I'm cross multiplying, so notice I get 0, that's also going to give me 0. Same thing here, we got 0 here, 0 there, so we cross multiply, also going to get 0. Now typically you don't have to put 0. I'm just kind of doing it just for the purposes. You don't have to put a 0 in front of a unit vector. Remember, a unit vector has a magnitude of 1. So if you multiply by 0, you just get 0. But I'm kind of just doing it, kind of just show you how everything is done. So it's going to be 0i minus, again, 0j. And then we'll have plus. And then we're going to do the same thing over here. So we essentially going to have to multiply here. So it's going to have 5 times 3 minus 3t squared multiplied by the 30. Again, if you want to distribute the 5 back in to make that a little easier, that's fine. But we already know what the answer is going to be, because when we took the dot product earlier and we simplified, we know what we got. So this is just going to be plus 150, 3 minus 3t squared. And it's going to be plus 900t squared. Okay. And then that's what we get for that part. And then we have to multiply that by, okay, so it looks like we got the 30t multiplied by the negative 30t. So again, when we were over here in the first part, when we took the dot product, remember that we ended up getting 225t to the 4 plus 450t squared plus 225. So here we'll get 450, basically minus 450t squared plus 900t squared. We simplify this. Again, you don't have to write those out. I just kind of was just doing it for the purposes. So now we got the cross product of the first and second derivative of the acceleration vector r prime and r double prime of t. Then we'll compute the magnitude in just a second. And so in this particular case, we're just going to end up getting, okay, we're just going to end up getting 450t squared plus 450. Okay. Or if you want to, you can factor out a 450. Again, remember what the magnitude of the first derivative of the acceleration vector was. It was either 15 squared plus 15, or if you factored out a 15, or then it would just be 15 times t squared plus 1. So the reason why I factored it out is because if we get 15 times t squared plus 1, that's the same thing as 15 t squared plus 15. If we distribute the 15 in, if I factor out here, I'd essentially get another t squared plus 1. If I actually factor out a 450, that'll make it easier to cancel. So essentially this becomes 450. And then we got t squared plus 1, and the unit vector k is there. So now we compute the magnitude of the cross product of r prime and r double prime of t, which is the first derivative of the first and second derivative of the acceleration vector r of t. So in this case, again, it's the square root of the sum of the components squared. We know that when we square 0, we're going to get 0, so there's no reason to write those in there. So all we got to do is just write in the 450, the t squared plus 1, and then we just got to square all of that, because again, when we square 0, we get 0. So there's no reason to really put the zeros in there, other than, you know, just wasting some time doing some handwriting, so you don't really do all that. And then we simplify everything down. So again, this is just going to end up giving us, I should have done it this way. Let me do it this way. So this is essentially what we have. So we got t squared plus 1, and again, that's being squared. So essentially what we're going to get here, remember, anytime you're squaring, when you're taking the square root of something squared, you get whatever's being squared. So in this case, I just get 450 multiplied by t squared plus 1. anytime you take the square root of whatever's being squared. So now the normal component of the acceleration vector a sub n, and it's essentially the same thing. So we'd have 450 multiplied by t squared plus 1. The magnitude of the first derivative of the acceleration vector r prime of t was essentially 15 times t squared plus 1. And that's effectively the purpose of factoring that out once you took the first derivative of the acceleration vector. And now we can simply do some simplifying to attain the normal component of the acceleration vector. We do some simplifying here. So let's just simplify those two down. We know that the t squareds plus 1s are also going to cancel out. 450 divided by 15 is 30. So therefore, we can say that the normal component of the acceleration vector is simply 30. So for our final answer for this problem, we now have obtained the normal component of the acceleration vector and the tangential component of the acceleration vector. So for our tangential component of the acceleration vector, so component, I'll post a picture of the answers as well. So the tangential component of the acceleration vector, what do we got for that? That was just 30t, remember? So we got 30t. And then the normal component of the acceleration vector, so you got normal component, was just going to be, or a sub n is just going to be 30. And that's how you compute the tangential and normal components of the given acceleration vector. So for the most part, like I said, if you're familiar with the process of taking derivatives and the dot product, the cross product, all that good stuff that you learn about in multivariable calculus, then hopefully this won't be too hard to pick up on. But this is how you do it. It did take a little bit of time, so I apologize about that, but I just kind of wanted to demonstrate how everything was being done. So that is your answer. So I'll post pictures of the solutions for everything. So let me know if you got any questions about what was done. But other than that, I'll see y'all next time.